Hello, good afternoon, and welcome everybody to another session of Asset Weekly Lecture. And we are privileged to have here very prominent space research scientist, Dr. Girish. He works as a deputy director on a science mission program of ISRO. So all AstroSat and likely astronomy satellites and anything which is astronomy related space science goes through his office. And he also manages AstroSat for last 4 years now.
Yes.
Yeah, 4 to 5 years. And of course, he had a long history of having been visiting TFR. He did a postdoc also, if I remember correctly, in 2006 here for a year.
5 to 6.
5 to 6 he was here. And he has worked on lots of astronomy satellites in collaboration with TFR. RT2 mission, he was one of the person who initially started with. Even he was associated with AstroSat in the very start phasing around 2007 to 2009 to 10 time frame when AstroSat was getting fabricated and being directed. And he is, of course, did his MSc from Bangalore University and a PhD, subsequently his PhD from Indian Institute of Astrophysics. Indian Institute of Science in 2005. And as I mentioned already, he did his postdoc here for a year. And of course, he had worked on RT2 missions and AstroSat and Chandrayaan-1 mission as well, at the initial phases. And he, of course, as I already mentioned, he is a space science researcher with interest in X-ray studies of catalytic variables. And he has published more than 52 papers in national and international referred journals and conference papers as well. And of course, now he is doing a lot of administrative work from ISRO sites in making sure that the futures of other missions and things also will be taken care. And he also is quite frequent writers in public journals and newspapers and articles in local Kannada language as well. Without further ado, I request Girish to please.
Thank you. Yeah. Thank you very much. You can hear me, right?
Yes.
Thank you very much for the nice introduction, Parag, and also for inviting me for giving this asset colloquium. So AstroSat will be celebrating its birthday tomorrow. So 9 years back on this day, AstroSat was launched from Sriharikota, that is SHAR, what we call it as Sriharikota High Altitude Range. It is in Andhra Pradesh. So it was launched for 9 years back tomorrow, okay? And so it is a real national and international collaborative project. So the reason why I'm saying that is AstroSat carries a total of 5 payloads. I will be talking about all the 5 payloads in the subsequent slides. Out of that, 3 experiments or the scientific payloads came from TAFR. So large area X-ray proportional counter, cadmium zinc telluride detector, and then soft X-ray telescope. 3 science payloads and also 1 auxiliary payload called charge particle monitor. 4 of them came from TAFR. And then in addition to that, other scientific payloads came from Indian Institute of Science, Astrophysics and IUCAA. And 1 of them came from URC. You can imagine that only 1 science payload came from ISRO actually. And not to mention that ISRO is involved in almost all the payload development. Supported them in mainly thermal and mirror making and others. And in addition to that, we also have 2 international collaborations. One is University of Leicester, which was involved in SXT, and then Canadian Space Agency. So that is in UVAT. So I'm sorry to say that the one person who was involved from Canadian Space Agency, Professor John Hutchings, so he was the one who collaborated in the UVAT plan. So we lost him last week. I just wanted to inform you that. So coming back to, before going to AstroSat, so AstroSat's one of the major capabilities of AstroSat is simultaneous multi-wavelength observations covering from visible NUV, FUV to very high energy X-rays. So why do we need multi-wavelength? So this is for the very basic thing. So multi-wavelength means any other wavelength gives us another probe to actually probe the cosmic sources. In this particular example, so when X-rays was discovered, that gave us another probe to look inside our body. So similarly, so the multi-wavelength also has a lot of useful things. like multi-wavelength observations are required to probe a source completely. I will not say 100%, give maximum information. So just to give, just for completeness sake, so electromagnetic spectrum, there is over a very large wavelength of frequency band from radio to hard X-ray energies. So just to tell why exactly we need multi-wavelength. So this is all, you are all familiar with most of this stuff. Just bear with me for a few minutes. So this is a picture of our sun, and those spots are sunspots. Okay. Oh, they are sunspots. Okay. So these are because the temperature there is slightly lower than, few hundred degrees lower than the photosphere surface temperature. But the same spots, when seen in different wavelengths, actually gives you different information. For example, on the left side, it is in IR, infrared. You can clearly see that the emitting area is much larger than whatever we see in the optical area. That clearly shows that something else is happening there. But when you come to high energies, for example, in the last one is X-rays. So X-rays and UV, the things are completely different. Those which were at a lower temperature or less flux or spots are now very bright here. And the ones which are bright there is completely very, very dark here. So that clearly shows that this is not following a simple black body radiation. So something else is working there, else is in action there. So extending the same thing for a few more targets, this is a very famous neutron star, fast rotating neutron star called as Crab pulsar. This is rotating at 33 times per second. One of the best dynamos ever seen in our whole universe as of today. So the actual shape and this information about the neutron star comes from the X-rays, which is on the top left. I'm sorry, this one is not working. I don't know. So top left, and that clearly shows that it is acting like a rotating top. So, but we need other wavelengths to actually get the full information what it is. And I could not resist putting the crab as observed by UVAT. So this tells you why we need multi-wavelength observations. So next, coming to our AstroSat. As I mentioned earlier, so AstroSat carries totally 5 scientific payloads. These scientific experiments we normally call as payloads. I might be interchanging the two words. So out of them, 4 are collinear, pointing at the same point of the sky. So in that way, we'll be getting simultaneous observations from that particular field of view. So these 4 are large area X-ray proportional counter, which was developed at Tata Institute of Fundamental Research, and along with the RRI. So it covers a energy range of 3 to 80 keV and is capable of very fast timing observations along with coarse spectroscopy. So then soft X-ray telescope, this is again realized at TFR and in collaboration with the University of Leicester. And this covers 0.22 to 80 keV, and this is capable of giving imaging along with spectroscopy and timing. And just to tell you, most of the X-ray instruments are capable of giving both timing and spectroscopic information. And then cadmium zinc telluride imager, this is again another payload from Tata Institute of Fundamental Research. So this is a hard X-ray instrument and it's a imager. It covers from 20 to 30 keV to 250 and above keV energy range. And then UVAT is ultraviolet imaging telescope, which is a workhorse of AstroSat as of now. More than 50% of AstroSat publications are from UVAT. And this covers 1 to 1.5, and it has one of the best spatial resolutions as of now. And finally, scanning sky monitor. This is from URSC. This acts like a all sky monitor. So this has 3 proportional counters arranged such that at any time it can cover almost 1/3 of the sky. And since it is rotating, it can give you more than one hemisphere in one orbit. So the total weight of the spacecraft is around 1,450 kg, and as I mentioned, it was launched using C-23 PSLV launcher on 28th of September 2015. Okay, so I'm sorry, before that, I'm yet to get used to this. Okay, so ISRO, so not only helped in realizing many of these payloads. In addition to that, the spacecraft and operations and normal maintenance and everything is taken care of by Indian Space Research, the organization which I am a part of it. And the ground software is developed at multiple places. Now ISAC, the name is changed to URSC, UR Satellite Center, Space Application Center. These two are from ISRO only. And Tata Institute of Fundamental Research, Raman Research Institute, Indian Institute of Astrophysics, IUCAA, NCRA and PRL. In fact, if you see this list, you can see that almost most of the research institutes which are involved in astronomy research are also involved in AstroSat. And to encourage usage of AstroSat data, ISRO has set up a support cell at IUCAA, Pune, and that is actually taking care of all the user support. So coming to ultraviolet imaging telescope, this is Professor S.N. Tandon was the project manager for this particular payload. He is from IUCAA. So it consists of two twin telescopes, each one having a 40 centimeter RC telescope mirror. So it has the best spatial resolution as of today. It's almost 1.2 arc seconds. And it has it can make observations in multiple narrow band filters. So it can give you coarse spectra also. So NUV carried 5 filters, UV another 5 filters, and visible 3 filters. So these are some of the pictures. This is pictures from NGC 2336 taken from UV8. So just to show the effect of resolution. So in comparison to galaxy image of the same galaxy, you can clearly see how much better is UV80. And because of this and the large collecting area of 40 centimeters, so it is doing wonderful science. And these two telescopes for each 40 centimeters one of them is mated to FUV sensor and another one is mated to 2 sensors, visible and NUV, with a beam splitter. Okay, the beam splitter splits the incoming light into NUV and FUV. Unfortunately, a few years back, NUV stopped working. So, and visible is used only for tracking purpose or image reconstruction, and hence only FUV is working now. And just to mention here is that whatever the 1.2 arc second resolution, I am also helped in that one. So I actually derived the diffraction of all the fiber bundle so that we could reach 1.2 arc seconds.
Hey, Girish, UV80 also has a Grism spectroscope.
It has two. It is there. I'll be showing that. So that started coming only recently. See, Grism data started used only 6 months back. So till earlier it was grating spectrum. It has also Grism. I'll show that result.
Actually, it is grating only, not Grism.
Coming to soft X-ray telescope. Soft X-ray telescope, primary manager was Professor K.P. Singh, and currently Sudeep Bhattacharya from here is taking care of SXT, Payload Operations Center. And we are all familiar with X-ray bending and others. So like optical, it is very difficult to bend X-rays. So most of the times they simply pass through the material. So to actually bend, what we have to do is like we have to make the X-rays fall at a glancing angle, as if we are skipping the stones or something, rocks over water. Okay, whenever you just throw it along the glancing angle, it just keeps skipping. I didn't know that there is an international competition for skipping, and the highest number of skips they have got is around 7+, I think. So using this principle, so there are multiple mirrors are actually arranged such that in a glancing very shallow angle, so that all the X-rays get reflected onto the focus, gives a focus, and this can give a focus of around a few. Initially the idea was to get a focusing of around 1 arc-minute resolution, but unfortunately we could get only 2 arc-minutes resolution with a very, very broad wings, so almost 10 arc-minutes. So this is very good for X-ray binaries, because most of these X-ray binaries are bright and they will lead to pile up. So hence Chandra and XMM cannot observe bright X-ray binaries. So this gets rid of that particular problem, and hence it is very useful for studying bright objects up to 0.1 Crab. So this is large area X-ray proportional counter. The name word large is a opt name because when it was launched, so with the 6,000 centimeter collecting area, effective area, so it was one of the largest this detectors at the time of the launch with using 3 proportional counters. So this Parag is actually now currently taking care of it. Earlier, it had multiple project managers, Professor Yadav, then Professor Antia. Now Parag is taking care of it. And this is pictures during realization of design and developing of large area X-ray proportional counter. So you can clearly see the size of the proportional counter just for comparison, the developers. Okay. So it has 3 identical units, and one of the best things is it can do very, very fast timing observations, almost 10 microseconds. It covers a broad energy range of 3 to 80 keV, and it provides you very low resolution spectroscopy of around 12% at 22 keV, and it is non-imaging. So it covers, gives you a field of view of around 1 degree by 1 degree defined by graded collimator. Currently, only one of the 3 proportional counters are working, so other 2 are switched off. So cadmium zinc telluride imager, again the same problem for imaging because we cannot bend X-rays, particularly hard X-rays. So we use a novel method called coded mask, where we actually photograph with some coded mask and see the shadow, and we reconstruct the images. So this covers 20 keV to more than 250 keV, but beyond 100 keV, this acts like an open detector. The collimator will become transparent beyond 100 keV, and this transparency is used for the advantage of cadmium zinc telluride in that way that it acts like a open monitor, like almost 180-degree coverage it will have. This is very good for detecting and following up the transients, so which can happen any part of the sky, and also for gamma ray bursts, which are very randomly, it will just happen randomly. And with this, so CZTA has actually observed and studied more than 650 gamma ray bursts as of now. In addition to that, so even though it was not designed as a polarimeter, so after the launch, just before the launch, they started working towards actually using it as a hard X-ray polarimeter using Compton polarization method, and with that they could actually detect and study X-ray polarization, hard X-ray polarization in many sources. So coming to the last science payload, scanning sky monitor, as soon as on the day of opening of starting of this scanning sky monitor or the first light, we could actually catch GRS 1915 changing its shape, these phases. So that was a very good result. And this has a one-dimensional coded mask. So along the code, you can get almost up to 10 arc minutes angular resolution. This is used for transient studies, alerting the transients. So AstroSat operates as a proposal-based observatory. So there are mainly 3 types of observations carried by AstroSat. One is the proposal, one is based on the proposals, and the second one is what is called as target of opportunity, and third one for calibration of proposals. So all these proposals are actually starts with the proposer writing a proposal and submitting to AstroSat proposal processing system called APPS. So from the APPS, it goes back to multiple committees to review the proposals for its science merits along with feasibility, technical feasibility. So these committees are constituted by ISRO itself. So AstroSat Time Allocation Committee and AstroSat Technical Committee. And then from that one, selected proposals are sent to scheduling. So where they generate the necessary commands for observations. But AstroSat is one of the complex mission ever taken by ISRO. And it has to be moving from one source to another, and along with that, each of the 5 payloads has multiple ways of observations, multiple configurations. So all these things has to be taken care, and also we have to worry about the safety of it. So it cannot come within 90 degrees of sun because that can actually destroy the UV80 sensor. Also, whenever it is moving, the ram angle has to be away from the moving direction. Otherwise, it can puff through the electron, that whatever the particles there, and even one layer of mono layer of particles can bring down the UV-AT sensitivity by almost 10 to 20%. So to avoid that, it has to always looking away from the dime angle. So lot of constraints are there. So because of all the taking care of all these constraints, so we have to make observations. And also it is giving 1.2 arc seconds of spatial resolution. So that means that the pointing accuracy should be of the order of that or slightly better than that. So that means that pointing has to be kept very, very stable. So all these things comes into picture. So taking all this into consideration, the commands are generated. Commands will be uploaded to spacecraft, and the data, whatever the data which comes, it will be combination of all the 5 science payloads plus the auxiliary payload plus housekeeping parameters. So once it reaches the ground, so this is split into different payloads along with respective housekeeping parameters, and then that is sent to payload operation centers. Individual payload operation centers, for example, LAXPC payload operation center is in Tata TA for itself. And then these payload operation centers validate the data, and if they think that this is scientifically useful, then they send back the level 1 and level 2 data, which will then go to this data disbursement place called web browse. There, this, since it is acting, it acts like a proposal based observatory. So there is a lock-in period of 1 year for the proposal submitted, and the target of opportunity observations do not carry any lock-in period. So from then the data goes to users based on the lock-in period. So some of the AstroSat advantages, just I am repeating many of them. So it is in the equatorial, very close to equatorial orbit, at a 6-degree inclination. This is to make sure that the effect of South Atlantic anomaly is minimal. We are not saying that it's zero, it should be minimized. And then it gives you continuous time tag data in almost all the instruments, all the 5 instruments, and some of them are to very, very high accuracy of microseconds. And they have the AstroSat has the observation capability of very bright observations, and I mentioned that UV-AT has the best spatial resolution as of today in UV. So combining all these things, and X-ray polarization is an added bonus. So combining all these things, I'll start with why we need what we can do with multi-wavelength observations. So some are using the full capability of multi-wavelength capability of AstroSat. So we can study blazars, CFIRs, tidal dissipation events, and change log AGNs, etc. And along with that, X-ray binaries like black holes, neutron stars. Even though we mention white dwarfs, that is cataclysmic variables, unfortunately using LAXPC, so we are yet to model the low when the counts are very low. So the background modeling is not up to the level, so we cannot do much with white dwarfs. But black holes and neutron star binaries, we can do a lot of science. So just to give an example of grating spectra, you are asking for a grating spectra. This is for IC 4329A. So this is the first paper on grating UV-AT grating spectra from Gulab Devangan and his colleagues. Okay, so it can clearly see that the lines can be, you can identify multiple lines and other things when combined with this with 4 spectra with multiple filters. This is a almost 4-day observations, I think. Okay, so you can do you can get a lot of information about the spectra and emission. So in this particular case, the power law spectra slopes are very less, so indicating that these are redder redder, and using these temperatures derived and other things, so they found that these disks are truncated, so they are not extending up to the black hole. And coming to this another example of multi-wavelength thing. Okay, so in addition to the spectroscopy, it can also do very good timing spectra, and also this is used for studying the time delay or time lag between multiple wavelengths. So with a 4-day observations on NGC 4051 and using cross correlation functions, so it was found that UV and X-rays are the time lag, the UV lags to compare to X-rays by almost 14 kiloseconds, and while NUV and NUV lags FUV by almost 3 to 4 kiloseconds. So they say that this is because of the change in emission geometry and others. So this is one of the major results from multi-wavelength studies in timing studies. So in addition to these agents, we can also do a lot of studies of black holes, particularly black hole binaries and others. So this is one such black hole binary. So you can clearly see the outbursts. During the outbursts, you take individual outbursts and plot a spectra from X-ray luminosity versus spectral hardness. It shows multiple phases. So like it can be soft spectra, it can be soft intermediate, hard intermediate, and other things. So when you plot this one, that gives you an idea of how exactly the emission is happening and accretion about accretion region. So the main emission from a black hole consists of emission from accretion disk, corona, and from reflection. We get all the three together, and AstroSat can probe all the three regions and give you information about individual places. This is about the spectra. And similarly, we can also do very, very fast timing studies of these black holes and neutron star binaries. And with that one, we can actually study whether it is a periodic or quasi-periodic or aperiodic. So if, for example, if you can study quasi-periodic oscillations in the kilohertz and others, so that gives you some information about the accretion geometry and even the size of the accretion disk. Okay, and the size of mass and spin of the black holes also. So, and even in the spectra, I didn't show you, some observations have actually done for studying the variation of the 6.4 keV K-alpha line, iron line. So with the timing of lag species so good and so good, depends on the kind of, say, for example, if you are observing white dwarfs, you will see a lot of other lines, but this one iron line is the most dominant one. So if you go to SXT, there are multiple other lines also. So we are say whenever it is a relativistic broadening, so that happens mainly in iron line only. I missed the word relativistic broadening and that's it. Okay, so we using the lag species data. So the precise measurement of Crab pulsar spin down was carried out up 36.3 nanoseconds per day. That kind of accuracy was obtained using lag species data by Professor Dipankar Bhattacharya and his colleagues. So you can clearly see that in multiple wavelengths or energies, 2 to 10 keV, 10 to 30, like up to 250 keV. So these many bands are available with AstroSat, which is nowhere, like it is not available with any other observatories. When I say any other observatories, I'm talking about simultaneous. As a different observatories, they do have, but this coverage, simultaneous coverage, is not available with anybody else. So this is one of the major results from AstroSat. Even though AstroSat is not meant for any X-ray polarization studies, I mentioned that CZTA was converted, like whenever the photon falls on cadmium zinc telluride, so it has multiple pixels. So whenever the photon falls here, then the ejected electron, actually it goes along predominantly along the polarization angle. So whenever you do you do observations for a long enough time, and you take the count, measure the counts in each surrounding pixels, from that you can reconstruct what is the polarization angle, and you can calculate the polarization angle of the source beam. So using this method, so polarization measurements were made for multiple sources. This is one of the first observations. This is from Crab. So Crab was the only source till for last 5 decades which showed X-ray polarization. Okay, and AstroSat CZTA has shown that the polarization comes not only from the beam, even from the off-pulse region also there is X-ray polarization properties are there. So that is explained by Chen and why exactly you expect polarization from non-beam off-pulse region also.
What is polarization signified here?
In this particular case, X-ray polarization signifies the magnetic field, and its angle. In this particular case. So gamma ray, so as I mentioned that cadmium zinc telluride is transparent beyond 100 keV, means that collimator is transparent beyond 100 keV. So it allows us to actually study multiple gamma ray bursts. And with that, one of the actually AstroSat's first observation gave us a one gamma ray burst. So it started with a gamma ray burst. As of now, it has actually observed more than 640 as of last week back, 1 week back. Okay, regularly it will be observing, and in many of them, more than few dozens, it has even detected a hard X-ray polarization and studied the hard X-ray emission, hard X-ray polarization from these gamma ray bursts. And also, so it can also work as a gravitational wave counterpart for a gravitational wave event. So when the first gravitational wave event was detected, so from 5-6 years back, unfortunately, AstroSat was looking at the other direction. So we could not see that. But the funny thing is, even then, actually, it helped this one LIGO to actually triangulate that. So by reducing that, by actually removing the chances of seeing that gravitational event from so many angles, that it has reduced the search space to 1/3. So it constrained that. So even though it was looking at the other side, it helped in constraining that one and improving the accuracy. So just coming to the science highlights, as I mentioned earlier, like simultaneous multi-wavelength capability and all these things. So we have studied multiple types of sources, starting from comets, stars. Even we have AstroSat has observed and studied coronal emission from other than sun, outside another star, Proxima Centauri, and nearby to distant galaxies up to almost like up to 9.3 billion years, and neutron stars, white dwarfs, all these things. In addition to that, we have actually studied even pulsating sources like pulsars. So I would like to actually bring to you like some of the major science results or the discoveries from AstroSat. The first one is it has solved a decade-old puzzle. I'll actually talk about some of these later in my edition. And as I mentioned, it studied coronal emission in stars, particularly Proxima Centauri, and blazes, thermonuclear bursts, very, very fast thermonuclear burst happening within minutes. Okay, and spin measurements of black hole. These two pictures, you can clearly see that left one, this is a supernova explosion, which AstroSat caught in 2024, May 19, 2024. And on the second left side is a similar image from same AstroSat taken in 2016, clearly showing the presence of the supernova. And the bottom one is what is called as atoms of peace. Don't ask me why that name came. So as of now, AstroSat has done totally 1,800, it has observed around 1,800 targets, over 3,200 observed waypointings, and the currently Cygnus X2 is undergoing observations. And these are the coverage throughout the universe, how we are actually covering. AstroSat is making observations. So I mentioned that just in the last slide, I mentioned that it solved a decade-old puzzle of a source, which was puzzle. The puzzle was, so there was a source which was bright in both UV and IR. So typically whenever you see a source, so you assume if you use a blackbody radiation, you get only one peak. You are supposed to get only one peak. Either it should be faint, cold, or it should be very, very hot. But in this case, there are two peaks. One is an IR. It was bright in IR and also bright in UV. So for 2 decades, this was not at all actually solved. Then AstroSat, within 1 month of operation, it peered into that and it found that there is a hidden white dwarf, so which is actually responsible for the hot component of the spectrum. So it happened within 1 month of that. So this is from IAA. And then this is a very famous butterfly nebula. So this butterfly nebula, when seen through AstroSat UV, so it clearly shows that the extension is almost 3 times more than the butterfly nebula itself. In this image, this is the original, whatever the optical image looks like. This looks like a butterfly nebula, and this blue one clearly shows that this is the emission from the overall butterfly nebula, taking this into almost 3 times more than the butterfly nebula itself. This is the extended emission from AstroSat. And then Ayuka team observed very, very distant galaxies under a survey called AUDF, AstroSat Ultra Deep Survey. So, and in which they found that one of the stars, which is around at 1.42 redshift, they detected UV photons from those targets. So earlier it was this entire redshift range from 1.2 to 1.2 point something is supposed to be a desert. So you do not expect any radiation in UV in that range, because they are so far, all the radiation from that will be just observed in between. So there was they used to call it as a desert. But then UVAT with its high collecting area and a very good spatial resolution actually could observe leaked Lyman alpha photons from a galaxy which is 9.3 billion light years away from Earth. And then this is from TAFR. So Sudeep Bhattacharya and his team has actually observed and discovered one black hole binary which is rotating at maximal possible spin. Okay, that's they discovered that. And then, so this is from NICER, Mohali. So Aruberi and her team has actually observed one neutron binary, where within 15 minutes of observations, there are multiple thermonuclear bursts. Okay, so we all know that if they consider a source, so it will be accreting matter. At some point, this matter will reach to a level where the nuclear fusion can start. And once the nuclear fusion starts, it's like a bomb, like in the Deepavali, whatever the bombs you explode, something like that, it will explode, and then it will wait for enough material to accrete. But that enough material is happening within 15 minutes, 3 times. This is a very, very rare occurrence. So this is studied by AstroSat. And then gamma ray bursts, these are the number of gamma rays as of last week. It was around 640 gamma ray bursts are observed by AstroSat. Which one? Sorry,
top left one. All your observation were not able to find the
yes, hidden white dwarf.
That taken by some point AstroSat has seen. Some other mission or someone else has seconded this.
The problem with other missions are no, other mission is a galaxy whose spatial resolution is more than 5 arc seconds, and its collecting area is also less. So it was unable to actually do that. Okay, so even though AstroSat is very, very successful, so ISRO wanted to encourage more and more users of AstroSat, and hence ISRO started a limited funding. So every year we give some 10 to 12 projects funds to utilize AstroSat data. So it involves JRF salary plus computing and limited travel within India. And totally there are 30 projects. As of now, we have actually funded 30 projects, and another 10 we are going to release maybe in April, May. And this has a full coverage. If you say Kashmir, say Kanyakumari, and Gujarat to West Bengal. So we are covering almost throughout India. And more than half of them are from universities. Okay, they are not from research institutes, they are from universities. And in addition to that, so ISRO has also set up a support cell to help in users from proposal preparation, proposal writing, to obtaining the data, analyzing the data, and even interpretation. We regularly conduct workshops. Sometimes some of them are short periods, say 5 days to 1 week, and some of them are very, very long. In addition to for hands-on training of AstroSat data and science interpretation. In addition to that, we also have a lot of webinars and other way of helping users. And if any user need any help, all they have to do is they have to write a mail to AstroSat help, and immediately it will be tackled. So coming to almost my final slide. So when we completed the 7 years of AstroSat, so their newspaper said that, so AstroSat has fielded over 275 research papers. So that was 2 years back. Now if from India alone, the number of publications has increased to 329. All these are refereed publications, and totally other publications like GCN circulars, astronomers telegram, and conference proceedings, all the others, they are almost like 1,150. These are from India alone. Okay, and PhD thesis, AstroSat data has contributed to around 338 theses as of 2 months back. So currently, the total number of publication is more than 440. This was last month. In September alone, another 20 plus got added to that. So the total number of publications are very close to 465 from AstroSat alone. And then we have extensive user community, more than 1,800 users from India alone. When I say users, these are the registered users. Most of them may be just registered for fun. And we have international registration of more than 1,000. So in these international users, the maximum users are from in the top 3, US, Italy, followed by UK. Sorry, Canada. So this is a picture what we have taken during the first 100 days of AstroSat. So it shows most of the people who are involved in this AstroSat development. So the one on the left, this is the project director. This works. Okay. I don't know. Okay, so the one on the left in front of the AstroSat mirror, this one is Dr. Surya Kumar Sharma, SK Sharma. So he was the project director when AstroSat was launched. So next to 2 people after that is left to him is Koteshwar Rao. He was the first director, and left to him is Dr. Sita, S. Sita. She is the principal investigator of AstroSat even now. You have Professor Antia, S. Kumar, and almost all the payload managers are here, like Professor Tandon, Professor KP Singh, Professor Rao, Professor Yadav. So, and last Sita and next to her Ramadevi are the project managers of Scan and Sky Monitor. So this AstroSat success, I can say that after 9 years, so getting close to 500 publications, and everything happened because of the meticulous and hardworking teams. From ISRO, we have ISTRAC, where the data, spacecraft maintenance, operations, and everything happens, and the data also comes there. So data is segregated into different payloads and then made available for dissemination. And then ISSDC hosts the web browse, and all the other stuff takes care there. URO Satellite Center and Space Application Center helps us in maintaining the necessary software. And ATAC and ATC, these are the committees which takes care of the review process of the proposals submitted. Even the target of opportunity also goes through review. And payload teams and POCs at the different places. For example, TA for hosts Cadmium, LAXPC and SXT payload operation centers. IUCA hosts CZTA payload center. Like that, UVAT is at IAA. And science working groups, Professor Dipankar Bhattacharya is the chairperson of science working group. It meets every week, and we discuss how to go about further to optimize the science output of AstroSat. And then AstroSat support cell at IUCA. So before I end, I just want to flash these 2 images. This is the image from JWST. This is Stephen's Quintet. So taken a year or 2 back. And you can clearly see how good it is. And now the same Stephen's Quintet superposed with NUV and FUV data. The dark blue and pinkish color is, orange and pink color are from NUV data, NUV and FUV data, which clearly shows that this complements very well that IRR, JWST data. So we are almost at par with international observatories. Okay, with that I'll close. Thank you.
Girish, for giving a very good overview of what AstroSat is capable of and the efforts and the teams which were involved in it and the publication which is done. Open for questions. Anybody has, please.
If you see the Rao spectrum, the X-ray spectrum of Rao, which was CZTI, that spectrum, what you show the 60 to 80 kV, the band, if you go to the spectrum, it was by Rao's data. X-ray data. Yeah, see, right. The RAW.
No, no, I mean just.
One or two slide back, yeah. Yeah.
Oh,
See,
this is
yeah, that was right. Yeah, that was the right earlier. Yes, this is. So here you see some lines within the 60 to 80 kV or 80 to 100 kV,
that
right?
is the timing. It's a light curve.
Achha, it's a timing.
It's not
Okay.
spectra.
Yeah,
It's a light
spectrum.
curve.
That's what I was wondering.
So that clearly shows that where the GRB had occurred. Sorry, it's a light curve.
But is the understanding of at that energy, what lines you are looking at? With that
I-
high energy.
It is more than 250 kV. It's around 250 kV. I do not expect many lines around that. Maybe some other people may comment that.
Because those are the lines typically you have gold K X-ray lines, and some of the L and M X-ray lines will come, but that.
No, they will be very, very weak. So you have to have enough flux in that lines to be like detected here. And also, this has a energy resolution of I think around 9 to 10%. So at 250 kV, the energy resolution will be that width will be almost 20-25 kV. So if the line is, it will get smeared. Yeah, it will get smeared.
So if a target opportunity is identified, how long does it take for AstroSat to?
Okay, so
point
it's a very good question. The best what we have done is around 8 hours from the submission of the proposal to observations. We took only 8 hours. So two things happens there. One, you should be lucky. And the other one is like as soon as the proposers started writing the proposal, they contacted me and okay, actually I am responsible for the day-to-day activities. So they contacted me and the target of opportunity committee and everybody. So everybody were in the loop. As soon as it came, we could actually upload that information. And also what happens is that this orbit is almost 1.5 hours, 90 minutes orbit. So if we miss uploading the comments in one orbit, then we have to wait for another orbit. So it takes 1 or 2 orbits for that also. Taking all of this into consideration, the best we could do is something around 8 to 9 hours.
To subtract out the committee hours. No,
for that also we have talked about. For example, some of this TDE, so we want to make everything ready in advance and do, but then again it has to go through safety. Because UVAT has a very safety margin is very, very low. So somebody has to actually clear the safety. Unless and until you know the particular direction where this is happening and that direction is proved to be safe, it is not possible for us to take it up.
What does this pointing mean? You actually have to use signal to rotate the
Yes,
satellite.
yes,
direction.
exactly.
How well is that? How well can you control the?
No, they are fairly fast. For example, for almost 90-degree rotation, it will not take more than 8 to 10 minutes. That is all done, and even the pointing stability is also good. But sending the command to point is the problem. And the visibility, I said that visibility is only 8 minutes in this 90 minutes period. It can be only around 8 minutes, and being this one, so 8 minutes has to come in the office times. Otherwise, also we'll be in tough. So
that it should not be pointing towards sun or something.
Those constraints. That's why I said that safety concerns are always taken. The committee first has to clear that particular point. So then, if all the safety things and even then comes the star sensor availability. What happens is the stability. What he asked. So this using the star fields. There is an internal loop which correct for the jitter and others. So if there are not enough number of stars. For example, UVAT observations, we need minimum 4 stars in 2 of the sensors. If those 2 bright enough stars are not there, we will not be able to hold it there. And most of the times, for the safety reason, we will not observe that.
Yeah, very nice talk. Congratulations to the entire team for the huge success of the mission. I have 2 questions. One is regarding the gamma ray burst. AstroSat observed 640 gamma ray burst, and forming LAT that has observed several thousand gamma ray burst, but at higher wavelength. So, are there any coincident events?
But there cannot be any coincident events, right? The gap between Fermi and AstroSat is too high. Are there just
No, I'm saying in the time-wise, time coincidence. No, it could be that is a different wavelength that we understand.
no, not the wavelength. Even when Fermi was there, AstroSat, I don't think there was an overlap. Maybe I am wrong, but
Fermi is still operating. Yeah.
oh, then we don't know. Thank you. I'll just ask the person who is doing this.
Okay, all right. The second, what is the
Fermi lab. Oh,
yeah,
sorry.
Fermi land? Okay. The second question is, what is the current status of the instruments and how long you are going to operate AstroSat? Okay.
So, okay. So, LAX-PC, as I mentioned, only one of the LAX-PC is proportional counter is working now. So that means that 2000 square centimeters only. And then SXT is working normally, the way it was working earlier. So then UV80, NUV is not working, visible and FUV are working satisfactorily. CZTA is working satisfactorily. We actually disable 1 or 2 pixels. So whenever they go bad, as of now, the total number of pixels are less than 0.9% of the total, whatever the disabled is less than 0.1% of total number of pixels available. And then scanning sky monitor, only one proportional counter is working. Other one is working at a reduced this one. And then overall spacecraft has enough fuel to take it for 2 more years. But in between, not only fuel, some other things may also go wrong. So unless and until something goes wrong, so we are expecting it to work for at least a couple of years. We have enough fuel.
I think it lived more than its expected lifetime.
So
right?
yeah, just to say that this is designed for 5 years. It is almost close to double than that already. So we expect some mechanical failures. We hope that they will not lead to like stopping the operations.
Hi.
In your earlier slides, you had a design of the mirror. You were describing some X-ray mirrors, and you said that initial design was for 2 arc
minutes
kind of direction. But actually, you find out that it was about 10.
Yes.
Where was the problem? When you tested and you say 2, it is down on the ground, and then.
So we could not actually test it because we did not have big enough parallel beam to test that entire thing as a whole. This one, I think that's where the problem crept in. So we tested individual reflections and everything. Actual packing and actual putting them together, during that time they might not be aligned properly. So that may be the reason. And it's not that it is completely 10 arc minutes, only wings are 10 arc minutes. So because of that we might. And the overall, the particular design, whatever we have chosen, Walter 2 itself is like prone to this kind of things. We could not do. It's not that it cannot be tested. We could not do because we did not have enough by this one parallel beam.
Nice talk. I had a question. So you mentioned that these instruments can be used simultaneously, right?
Yes.
So in that case, every instrument would have its own sensitivity. So how does it decide on the exposure time duration, or how do you put a cutoff to the other instruments when some source is too bright for one of the instruments? How does it work there?
So that, UV80 will have that problem because UV80 normal integration is around 2.5 seconds, 2.36 seconds. During that time, if anything like UV photons are moved, then it might saturate. So, but the readout is around 2.36 seconds. So that means that up to 23 magnitude, we will not get any saturation. And others are reading out very, very fast. So unless and until the flux is more than the readout, this one, so we don't have that problem. Okay, so rarely we see any pile up. Okay, and also SXT, even though it says 2.2 or 2.3 seconds as the integration, it can do it very, very fast if you define windows. Instead of reading the entire CCD, if you read only a window, it can do much faster. In this way, you can mitigate all these pile up problems. So we do not see any. And most of the times what happens is the science is defined by one main instrument, either UV or X-ray. So others will give you auxiliary. So we modify, means the proposer is asked to modify the parameters such that the main science goal is achieved by that, but this will give you complementary data.
Yeah, okay, thank you.
Sure. One thing is like whenever we observe any UV80, So we make sure that in that field of view, there are no bright sources. So if there is a bright object detected, immediately it will go to this mode. It will reduce the the safety things are also features also built in.
So you said something about the the gravitational wave thing, and you said that if AstroSat would have looked at that, I mean, maybe.
No, we were looking at the other direction. We were looking at that
So
other.
if you would have a kind of partner or something else for the AstroSat.
It could have given much more information, but we were looking at the other direction. But that is
still unlucky, you can say.
That's what I said. We were unlucky that we were looking at that direction, but that also helped in actually like triangulating that first gravitational event. It reduced the total field of view by almost 1/3. So in that way, it was useful.
Yes, so as you said that certain proportional counters are not working right now. So can you know what is the major reason behind that? So like radiation damage or something?
It's not major radiation. So what happens is, for example, if I take LAX PC, it was filled with 2 atmospheric pressure. That big detector maintaining a 2 atmospheric pressure inside, outside vacuum. So it has to survey that. And we cannot use very thick windows because that will stop the X-rays. So the window has to be very thin. At the same time, it has to stop leaking out. Most of the times, this leaking out is the problem. And then, so that's
basically detector 30 leaked out after a year. So it has been for last 6 years. So we've been keeping it off since 2017-18. And LXPC 20 is working 100% as it is. And as he mentioned, DT10 has a very fine leak, but over the period of time,
9 years.
The detector has almost lost half the case. So it is still functional, but we cannot have energy calibration with it as dependently as we had done on the ground. So, but the timing analysis, DT10 matches with the DT20. So it still helps. So DT20 gives you full science data, and DT10 gives a collaborative timing signatures can be verified by 2 detectors. Energy, of course, can be done only with the 1 detector. If there is no more questions, thanks once again, Girish, for giving a very and thank you very much for giving it. And hopefully you can come back here and celebrate 10th year as well.
Thank you.
Everybody is welcome to have a tea with